Welcome to the first lecture of the second week of this course. Today we are going to discuss something called conditional expectation. Conditional expectation is the first most important thing that I need to discuss with you. The remaining part that I was discussing with you is something I was expecting that you had almost some idea about, but here we start with something very new, usually not done in standard courses of probability. Standard courses means courses which engineers usually take or economists take, etc. So, the exposition that I found most interesting was from a book called Probability for Finance. By Sean Deneen, published by American Math Society in 2005 under the series Graduate Text in Mathematics. So, what does conditional expectation mean? We will see by a very simple example. Suppose I take this of x is a random variable or s is a random variable which tells me how many times head appear when I toss a coin 3 times. So, how many heads in 3 tosses of a fair coin, repeated of course each, first toss, second toss, third toss, 3 repeated tosses of a fair coin. Of course, you know this is a binomial random variable. We have already we know that if n be the number of success, then np is the expectation given that p is the probability of success. Sorry, how many heads? So, just make a little correction. How many heads in 3 repeated tosses of a fair coin? So, it tells you that how many successes you have. So, here by success I am meaning the appearance of an head. So, I toss, so any of the 3 can come, head, tail, head and all these things. So, you know that expectation of this, because this is a binomial random variable, is nothing but n into p, where probability of success is half and n is 3. So, 3 into half, which is 1.5. What happens if I now ask you this question, find the expectation of S3 and find the expected number of heads that you expect if you make 3 repeated tosses of a coin, but with the knowledge now that the first toss is a head. So, now we are going to see how many tosses, you have 3 repeated tosses. So, how many heads would appear if you already know how many heads you are expecting, rather if you already know that the first toss is a head. What is the answer? This is interesting. You will see, now I know that the first toss is a head. I really have to look into the second 2 positions. This is given. So, here I can have head, head, tail, tail, head and tail, tail. So, means now I can have only one head appearing, remaining 2 are tail. I can have only 2 heads appearing, there is no tail at all. So, this one comes, or here head comes, then tail comes, then tail comes, then head comes. So, if S3 is 1, S3 can take value 1, it can take value 2, it can take value 3. It can never take value 0 because I know the first one is 0, right. So, when I am talking about 1 means these two tail has come. So, here among these 4 now I do not bother about it, it is already a known fact. So, I just have to look into this diagram. So, when tail comes, both are tail. So, among these 4 choices I have only one choice. So, there I have my probability is 1/4. So, 1 into 1/4, right. Now, if I have the situation where I have 2 heads which has come in 3. So, among these 2 one has been head. So, either head tail, tail head. So, any one of the 2 should appear with probability of the 4 this will appear 2 times. So, the probability would be half. You see the whole working changes. Now, 3 means I have got this. So, among all the 4 I have one chance. So, it is 1/4 plus 1 plus 3/4. So, it gives me 1. So, that this answer 2 1 plus 1 2 1 plus 1 2 this answer is 2. So, I leave you with to show that leave you with this question that if the first toss is tail, then what is my expected occurrence of heads? So, that would decrease. So, here my expectation increases when the first one is head. I am expecting that among the 2, 3 at least 2 would be head. Here because the first one is tail I am expecting at least among the 1 there will be 1 which will be head. So, you see once more information is available my expectation changes. This is called conditional expectation essentially. Now, how can I put this idea into a more rigorous form? See, this idea has been developed on a scenario where your omega is finite, your sample space has finite elements. So, your sigma algebra or the set of all events is the power set of that finite set. So, let us look into this scenario. So, we have, let me instead of u I am writing f, so that is what is usually written in finance books. So, let this be a probability space So, what is more interesting to know here is that I take that this is finite, the cardinality, the total number of elements omega is finite, that is, so my f is nothing but the power set so f is the power set of omega. Now, assume that strictly greater than 0 for all omega in the sample space. So, for every sample point, every outcome of a random experiment, the probability is strictly greater than 0, just like a head or tail scenario. And let A be an event such that probability of A is strictly bigger than 0 and we can take it less than or 1 or less strictly less than equal to 1, does not matter much. So, this is what I have assumed, and under this assumption I have to define what is called a conditional expectation. So, I am looking for the conditional expectation of a random variable x given that the event A has occurred. This is in some sense conditioning using a sigma algebra, because A belongs to a sigma algebra, and soon we will come to that how we actually condition over a sigma algebra. this is nothing but the very definition it will be x of omega and probability of omega given the conditional probability of omega given that the event A has occurred. This is exactly what will happen, this is exactly the definition. So, what is probability omega intersection A? That is probability of omega by probability of A if omega is in A and is 0 if omega is not in A. This is quite simple to understand because you see what happens when omega is in A, omega intersection A is omega. So, you have just P of omega by P of A, and when omega is not in A, omega intersection A is the null event, empty the impossible event. So, that time this will become 0 because this will be the null event. So, now coming to this board again, I am rubbing off what is in here. That is why sliding boards are so important, and this place has space for sliding boards actually. So, now I can write down the definition by putting in this place. So, what I finally get is expectation x given that the event A has occurred is summation omega element of A x omega P of omega divided by P of A, and this I can write as 1 by P of A, and symbolically you know that this sum is actually an integral. If we were not considering the discrete distribution or discrete setup, then this would be an integral. So, essentially a summation x omega P omega over omega element of A, but this is, we will always symbolically, even if we have sum, we would symbolically write this as. So, this is just a symbolical writing for the expression is just a symbolical writing for the expression x omega P of omega. Symbolical writing. Of course, you can move to non-finite spaces, which you will soon do, but this is just a useful trick to understand it. So, if you want to write about any other set, what about the complement? If I know the complement of A has occurred, then also this is nothing but the same. You can actually prove that there, you can just replace A with. Now, let us look at the sigma algebra which the event A can generate. That is the smallest sigma algebra which contains the set A. It should contain A, it should contain the empty set, it should contain the whole set, it should contain its complement. So, sigma algebra generated by A the empty set, the whole set A and A complement. So, if B, so we are just writing it, B is element of A. So, some sigma element B from this sigma algebra with PB greater than 0. So, we can write so, now observe that whenever B occurs, what does this means B occurs? Some omega belong to B has occurred. When you have random experiment, what is the meaning of B has occurred? When I say I throw out is odd number has occurred, if 1 occurs, odd comes out of the face, then the event that odd number has occurred. So, I can actually view this as a function. So, for any omega that I take in B, I can define a function like this, rather a random variable like this. So, for every omega in B, that is over the whole set B, whole event B, this is the value. So, it remains constant over the whole event B. So, I can, if I look at it like that, I am looking at a function which is constant over various events, then the conditional expectation itself can be viewed as a random variable. So, you see, because for it does not matter whatever, whenever any omega occurs, B has occurred actually. So, for any omega in B, this should be the story. So, whatever, once you know that B has occurred, so for whatever omega you take in B, this should be the story, this should be the answer. So, this idea that you can actually view the conditional expectation itself as a random variable is a very, very fundamental idea and is a very helpful idea. So, this is itself a random variable RV, and RV is just a shorthand for random variables. So, this will allow us to make shift from the standard probability space where we do not bother about the finiteness of omega and all those sort of things. So, first we will talk about a countable partition So, what is the meaning of a countable partition of omega? So, consider a sequence of sets, consider say Gi, I is equal to 1 to n infinity, right, 1, 2, 3 was G1, G2, Gn. So, consider Gi where each Gi is a subset of omega for all I in n, set of natural numbers. Then this Gi is called a countable partition if number 1 Gi intersection Gj is equal to phi for all I not equal to j, and number 2 union of Gi I is equal to 1 to infinity should give me back omega, the whole sample space. So, this is called a countable partition, and what we would now require is a sigma algebra generated by that countable partition, that you take elements of that countable partition, basically do not take intersections, because intersections would ultimately generate either the, if you take intersection with the same set, it will generate the same set itself or it will generate an empty set. So, basically if you want to take any non-empty set of a sigma algebra generated by this set, you just have to construct unions of this set of using some subset of n, could be finite, could be infinite, whatever, right. So, what we will be interested is in a sigma algebra generated by a countable partition, which will be a sub sigma algebra of F. naturally, because all the we are taking a subset, taking a subsets of A and generating a sigma algebra. So, consider a sigma algebra G subset of F and G being generated by a countable partition. Then we define it like this, and the conditional expectation of the random variable x conditioned on the sigma algebra G is defined at like this: at any omega, right, say omega n, or whatever, any omega is p g n integral g n x dp, because it is a countable, because it is generated by a countable partition, say g I, same one. So, given any omega, it must lie in one of the g i's, because omega is element of omega and this is a countable partition of omega. So, it must lie in one of the g i's. So, suppose take any omega, then this will happen. This is the way I define how you compute this random variable at the point omega if omega is element of Gn. Good. I will now, being a random variable, it is important to know that because I am claiming it to be a random variable, you should be able to prove that I leave this as an exercise to you in your assignments. So, of course, and this is true, you can prove this fact that this is measurable. An interesting thing is that if x is integrable random variable, that is it has a finite expectation, then this random variable also has a finite expectation, that is the conditional expectation conditioned on a sub sigma algebra of F, which is generated by a countable partition, has also got to be integrable. That can be proved, but I would not rather prove this fact now. So, this would be a part of the exercise. If x is integrable, I am expecting that you know what is integrability, though we have given some basic definitions. So, if x is integrable, then integrable means it has a finite expectation, because the expectation is expressed in terms of an integral, that is integral x dp, this is finite. Then E is integrable. That is, this random variable also has a finite expectation. This is important. Now, once we know this, we are now going to state a very important property of this random variable. This property essentially characterizes, and this idea actually allows us to move beyond sigma algebras, which are sigma algebras of this type. That is, we will now once you know this, once we know this result what we are going to state, using this idea we can give a very general definition of a random our conditional expectation as a random variable. That is, we can define the conditional expectation conditioned not by a just by a sigma algebra generated by a countable partition, but by any sigma algebra which is a sub sigma algebra of F. So, we are adding this important property, give a very small proof of this, and then that will wind up today's discussion. And this section is the first part of conditional expectation, and tomorrow we are going to discuss the general case and the properties of conditional expectation, and that is it. So, what does this proposition say? So, again G is a sub sigma algebra of F generated by a countable partition. Generated by a countable partition Gi. 1 to infinity. Assume, of course, this definition when you are writing, you are assuming that Pgn is strictly bigger than 0 for all n. So, without that you can't write this. Assume that Pgn, that is probability of each of these pieces of the partition, is greater than or equal to 0 for all n. Then E x by g, this conditional expectation, is the unique G measurable. Of course, when I am talking about measurability here, I am essentially talking about G measurability, is the unique G measurable, is a unique G measurable random variable such that random variable on the probability space, of course, such that for all A in G. So, on G, integrating over a set of G, subset of G, integrating over any element in G, any set which belongs to G over X is same as integrating over the conditional expectation. So, it essentially says that over G, conditional expectation and X are almost the same thing. So, over such a sigma algebra, X and conditional expectations, they behave in a almost similar fashion, their integrals are same, and this idea is actually used to extend to a higher. Basically, when you go to a case when you do not take this countable partition, you take this as a definition of conditional expectation. You see, this is how mathematics develops, because you do it for some simple case and then you know that it is not so easy to talk about the general case. So, you pull it up by taking the what you know for the simple case as a general definition, and that definition will always work if the case is simple. So, we will come to that later on. It has a lot of links with certain things called Radon-Nikodym theorem. So, let us give a proof of why this is happening. I am not going to prove the case for uniqueness because that is very simple. So, to prove the uniqueness, we really have to take any other y which for this the same thing happens, which will tell me that integral of this variable minus y dp would be 0. So, which means that if this function is 0, what does that mean? Function is 0 almost everywhere, that is exactly. So, that is the how you receive your uniqueness. So, we will just do the existence of this, that Okay, if I define the random variable in this way, the way which we have defined in this particular case, then this must be equal to this. So, proof, and that with that we will end today's discussion. So, I am just taking with this first with the Gn. Well, let us see why we are doing so. First, you have to understand why I am just taking first with Gn, because if A is any non-empty set in G, then A is always written as union M subset of n Gn, where M is a subset of n, could be finite, could be infinite, whatever. So, take some Gn from there and you are writing this Gn. M is capital M is a set which contains the indexes, which is subset, could be say 1, 2, 3, 4, 5 just. So, any subset of M. So, every A can be expressed like this, right, because the intersection, if you take intersection then empty, right. So, you can't, so every non-empty set has to be expressed like this. Okay, let us see what happens on this Gn. Now, you observe that on this Gn, for every part, if you look at the definition, this is a fixed quantity. You take any omega, any element of Gm, whatever omega you take, it will give you the same value. It is a constant on that Gn part. So, I can take to be some omega integral Gn dp, where omega is element of Gn. Now, what is this? This is nothing but probability of Gn, but I can again use this. I will write down the definition here, probability of Gn integral Gn x dp, probability of Gn, because this is nothing but probability of Gn, integral dp Gn is probability of Gn. So, what I will get here is integral Gn x dp. Now, if I am talking about integral A, so I can write this as integral union of Gn M subset of n. Now, because these are all disjoint, I can actually sum them up, sum each of the integrals. So, it is summation M subset of n, means summation over all the indexes of n, integral Gn and this summation, what is this? For each individual piece, this is nothing but this. So, this is nothing but summation M subset of n integral Gn x dp, which is nothing but integral union of Gn. Union of Gn is nothing but A. So, it is integral A x dp, and that is the answer. That is the proof. So, with this proof we end our discussion here today. Thank you very much.